There is a growing tendency in the AI industry to treat memory as an ever-expanding text file. By feeding an agent a massive prompt history, developers often inadvertently create a structural vulnerability. When instructions and data share the same context window, the model struggles to distinguish between them. A single malicious string hidden in a vendor email or a database export can behave like a new system command, hijacking the agent's logic. This leaves the system's operational boundaries in a probabilistic state. If the model determines its own memory scope, it can lose track of safety constraints or act on conflicting information simply because a recent interaction shifted its internal priority. For enterprise teams, mixing memory and data in the prompt creates a persistent security gap, one that persists even as models become more capable. The modern regulatory landscape creates a high bar for autonomous agents, specifically regarding how they retrieve and act on information. The EU AI Act mandates high levels of accuracy, robustness, and cybersecurity for high-risk systems. For an agent to be compliant, its decision-making must be predictable and resistant to external manipulation. Standard safety measures like system prompts and soft guardrails often fail these rigorous tests. Because they rely on the model's own interpretation, they cannot provide a deterministic guarantee of behavior. The Phoenix Daemon platform was engineered to address this specific compliance hurdle through its underlying architecture. The Phoenix philosophy moves memory away from the language model entirely. It replaces the context window with a strict, database-driven governance layer. Phoenix memory resides in a Postgres database, outside the model's reasoning space. It is data to be queried, not an instruction. Row-level security creates structural blindness between personas. A DevOps persona cannot retrieve data belonging to a medical persona. This is managed by a 5-layer stack. Layer 1 is the constitutional core. These 5 rules are cryptographically signed and immutable. If a request violates them, the system blocks the action before the model even begins to reason. Layer 2 manages persona-specific rules, while Layer 3 handles the working memory of active conversations, keeping state consistent across the fleet. The outer layers provide long-term stability. Layer 4 holds operator-curated common sense, and Layer 5 handles documents ingested through the RAG pipeline. By utilizing this database structure, Phoenix prevents the model from accessing unauthorized context. The data perimeter is enforced by code, not by a prompt. While internal memory is secure, autonomous agents must still interact with external tools and files, the most common path for hijacked instructions. Standard models often treat the output of a script as a new set of instructions. If a tool returns a command to ignore previous safety rules, a probabilistic model may follow it. Phoenix uses a trust envelope to prevent this. Data returned from an external tool is wrapped in a tag marking it trusted equals false. This tag persists as the data moves through the memory system. Whether in active use or stored, the untrusted label remains attached. The model is instructed to treat everything inside this envelope as data to be analyzed, never as an instruction to execute. Regulated personas add an additional firewall, the domain gate. This code-level classifier evaluates every request before the model sees it. The gate operates on a fail-closed posture. If the classifier detects ambiguity or suffers a timeout, the request is blocked by default. This approach forces the system into a predictable state, ensuring that external data cannot rewrite the agent's internal logic. Accountability is a central requirement of modern AI standards. Organizations must be able to prove why an agent took a specific action. Standard server logs are often insufficient for this. Because they are simple text files, they lack the cryptographic integrity needed to prove they haven't been modified. Phoenix employs a dual-write architecture for all audit events, recording actions to both a local log and a secure database mirror. The system uses an HMA-SEPT SHA-256 hash chain, generating a unique hash for every log entry. Each entry includes the hash of the preceding line, mathematically binding them into an unbroken evidence chain. Any unauthorized modification instantly breaks the chain, pinpointing the exact tampered character. In the database mirror, the agent's own credentials are denied update or delete privileges. The history of the agent's actions is physically protected from the agent itself. Verifying this history requires an offline operator key. The system is designed so that it cannot falsify its own record of behavior. This cryptographic chain provides the mathematical certainty required for internal audits and legal review. These security layers converge in the 16-stage cognitive pipeline. Every request must pass through these gates before any output is generated. The pipeline is designed to short-circuit malicious requests. If a prompt matches a refusal pattern or violates the L1 constitution, it's blocked immediately. The refusal corpus identifies these patterns at the pre-model stage, delivering a rejection at zero latency without the need for model reasoning. This structure ensures that safety is enforced as a technical requirement of the pipeline rather than a preference of the model. Effective enterprise safety relies on this structural physics, moving validation outside the model's internal judgment. The belief that smarter models will eventually solve their own security risks is a common oversight. Increased intelligence does not remove the fundamental need for boundaries. Deploying probabilistic systems in regulated environments creates a level of liability that many organizations cannot support. Phoenix moves in a different direction, emphasizing database isolation and cryptographic verification. The path to compliance lies in data architecture, even as the underlying models become more capable. By separating memory from reasoning, Phoenix provides the verifiable evidence chain necessary for the future of autonomous operations.